All right, well, welcome everyone to Introduction to Becoming a Qualified Energy Rater and Working with Qualified Energy Raters. Anytime you're upgrading a residential building, be it single family or multifamily, or building a new housing project, a qualified energy rater is going to play a key role in helping you reduce energy usage and costs, obtain financial incentives, and achieve a green building certification such as the LEED residential program. Now, outside of the United States, these professionals in many countries are very rare. And so while this webinar is intended to educate people anywhere on becoming or working with a qualified energy rater, we're also focusing on expanding this knowledge outside of the United States to help grow the green building movement within other countries. So regardless, please join us here to learn more. Now, before we get started, we want to say a big thanks to our supporting sponsor, Tamarack. Tamarack offers a wide variety of home energy savings devices and ventilation systems. They have attic access insulation and air sealing products and fireplace blocks to prevent air leakage, door vents, return air pathways to ensure good airflow. They have whole house fans to keep you cool while saving energy. And as a bonus, they also connect with our sponsor, Panasonic, for having all-in-one ventilation needs from exhaust to demand-controlled energy recovery and everything in between. Check them out over at tamtech.com to learn more. All right, this session is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator and co-speaker. My name is Brett Little, and I am the education manager here. This course is approved for multiple continuing education units, including 3 pillars of green in our Certified Green Home Professional designation, and new, hopefully we'll be doing more of this, international, the ICC. Yeah, excited about that. And then AIA, Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. Make sure to find that 5-digit passive house code within your certificate as long as you're appropriately logged in and here for the entire CU hour. All right, so again, introduction to becoming a qualified energy rater and working with one. The qualified energy rater, when it comes to a LEED residential project, is responsible for ensuring a baseline energy requirements are met on the project through the energy and atmosphere prerequisite minimum energy performance. In addition, the qualified energy rater must also inspect the project during construction and during the final, do the final test after construction. And so the energy and atmosphere fundamental systems testing and verification prerequisite is needed to use to update the energy model and verify what was in the plans in specs is both installed and installed properly with good quality. Not only does this ensure projects meet the minimum energy performance, but the qualified energy rater using the energy modeling can also help meet energy and atmosphere to optimize energy performance and verify additional energy efficiency and gain LEED points in the energy section. In addition to energy and atmosphere, a qualified energy rater is trained to ensure that the project is a healthy space for the occupants. And based on the LEED prerequisites in the environmental quality section, they may be ensuring the ventilation systems are functioning, designed and installed appropriately, and that the units are tight and not leaking air in between the units. So with that, I am very excited to introduce our main speaker here today, Charlotte Reed with the Energy Smart Institute, to get into these trainings and what is needed to become a qualified energy rater. So Charlotte, welcome. Thank you for joining us, and please take it away.
Okay. 1 second. Here we go. Hello, thank you, Brett, for having us here. Energy Smart Institute is a progressive educational platform that offers courses in an online, on-demand format. Our courses are available anytime, anywhere, whenever you choose to take them. With me today is Ken Reed, my business and life partner. You'll learn more about me in just a second, but Ken is the reason that I started working in building science. He is the original energy geek. He has a long-running resume, including teaching building science, solar and alternative energy, and energy efficiency. He has experience working in utility programs, performing energy calculations for large commercial structures, and running energy departments. He holds several certifications, including Senior Certified Energy Manager, Senior Certified Demand Side Manager, and Certified Sustainable Development Manager, or professional, actually. He has been recognized as a legend in energy by the Association of Energy Engineers, and he's here. He's going to be in the background. There he is. Wave, Ken. Answering your questions in the chat and the Q&A areas. I also have, I have been in the building science and energy efficiency world for 45 years now. We are an International Code Council, ICC preferred education provider, an accredited training provider through the Residential Energy Services Network, ResNet. I hold some certifications myself, an ICC HERS compliance specialist, certified residential energy inspector, plans examiner. I'm also a quality assurance designee for ResNet, out there making sure that things are done in a quality fashion. I am myself a certified HERS rater and a certified green rater, and I work on several ICC committees, writing all of the building codes and things like that, and working with them. I also have a history of running an energy rating company, running a ResNet quality assurance providership, and I used to run a LEED for Homes quality assurance providership as well. Brett reached out to me to partner with us in our training programs and provide the required education for the LEED qualified energy rater certification. So this includes education in building science fundamentals, air sealing inspections, and insulation inspections. And today I'm going to give you an overview of these areas. We'll be touching on these items at a high level, but if you decide to move forward and take the full training, then you'll get the deep dive for the full understanding. So, what are fundamentals of building science? Well, it's kind of in the name. We have building and we have science, and we are working in building science. Home construction has come a long way since the cliff dwellings to today's homes. We had homes that we were heating with wood. We had homes that did not have electricity. Only 8% of homes had electricity in 1908, and that was only up to 53% in 1925. And then we started putting bigger and bigger systems and more electrical consuming items. We discovered insulation, put insulation in our homes, then we had to work to try to conserve energy because we put all these electronics and things in our houses. Our construction techniques have changed from being a balloon frame to, in the United States now, platform framing for fire issues and things like that. But so our methods of construction have changed, our buildings have changed, and in that, we've wanted to look at the science of buildings. So since it is science, we have a lot of terminology that we use. We look at latent heat, sensible heat, latent heat of fusion, latent heat of evaporation. We look at things like other terms, heat, what is heat? What are BTUs? How do these things all come together? And it is the science of understanding a building and how it works and how everything in the building coordinates with everything else, how it all impacts each other. The basics, though, that we're going to talk about today are building envelope and air sealing are a major component of building science. What we want to try to do is control the building envelope, understand the building envelope, so that we can keep our conditioned air that we're paying to heat and cool inside that envelope and the outside air out. We have to understand, though, what happens with the with heat transfer. How does the heat transfer in and out of that building envelope? How do we lose the heat in the winter and gain the heat in the summer from outside? We look at air transfer. How is air moving through our building envelope, and what kind of issues is that bringing along with it? One of those issues would be moisture. How's moisture being handled in the building envelope and inside the building? How does moisture move through that building, and what kind of issues does it cause? What kind of benefit does it give us? And we have to know how to test our building envelope. We test for air infiltration, air leaking in and out of the building. And we test for duct leakage. So ducts that are transferring all that conditioned air, are they leaking? Are they not? Where are they leaking? Are they leaking to the outside world, or are they leaking inside the building? And what difference does that make? You know, how does that impact the entire structure and how everything works within it? And of course, as Brett pointed out, indoor air quality, making homes healthier. How do we keep the home healthy and keep the occupants of the home healthy? So indoor air quality is a big component of building science. The first thing that we have to understand then is that building envelope. What is that building envelope? Well, it is a boundary. It's a barrier between our conditioned air that we've just paid to heat or cool mechanically, and any place outside that we are not planning to heat or cool. That could be an attic or a garage or an unheated, unvented crawl space or a vented crawl space. It could be the outside air, ambient air that we call. But when we have that building envelope and we understand where it is, where we want to trap our conditioned air inside our structure, that is where we need to put our air barrier. Our air barrier is going to keep that air in there as well as it can. And it's also the location for our thermal boundary. Our thermal boundary is our insulation. That's what's trying to trap that heat either inside in the winter or outside in the summer. It can be kind of tricky to determine that the building envelope, exactly where it is. Sometimes spaces such as this basement that you're seeing on the drawing here could be an unconditioned basement, and then we would expect our insulation between the basement and the main floor. Or it could be unintentionally conditioned. Perhaps all our heating and cooling equipment is down there, and our ductwork is so leaky that it's becoming conditioned even though it has no vents. A lot of people get unfinished versus unconditioned confused. A lot of times there are unfinished spaces that are still conditioned, so they are still within the building thermal envelope. And there could be, plans that have some bonus space over the garage or other unfinished space. Does that belong inside our envelope if they're not going to finish it out, or outside the envelope? Where does it go? So it can be a little tricky to figure. Okay. We're also going to talk a little bit about heat transfer and the methods of heat transfer. These are things that you learn in building science. Heat can move in one of three ways. It can move by convection, which we've all heard of a convective loop where our hot air rises and cool air falls. That ends up moving heat around very quickly. It's when the molecules themselves of air are actually moving around in this convective loop, and the hot air molecules are rising and the cool air molecules are falling. So it's caused by differences in density in the air molecules. Radiation, that's the fastest method of heat transfer. You stand out in a sunny day and you feel the heat from the sun, and you step under a tree and you're instantly cooled off. That's radiant heat. It travels at the speed of light. It's very, very fast. It requires a couple things in order to move, and that is a gap of space and a temperature difference between the two objects. But radiant heat, it comes not only from the sun. You have radiant heat from objects in your home. Your computer has probably got some heat coming off of it. It's probably warmer than other objects in the room, and so it's radiating its heat to those other objects. It travels by line of sight, and it's blocked if there's any opaque object that stands in front of it. So if you've ever been at a campfire and you're sitting there nice and warm and you've got the fire warming up your hands and someone steps in front of you, all of a sudden you're freezing cold. If you're blocked, if the radiant heat is blocked, you're not getting it anymore. And then convection, or conduction, the one on the right. Conduction is the slowest of the three methods of heat transfer. This is when the heat transfers from one molecule to another. It's not like convection where the molecules themselves are moving. It's where the molecules start vibrating because they're warming up, and they vibrate the molecules next to them, and those molecules start vibrating and vibrate the molecules next to them, and the heat transfers and conducts from one material to another, from one molecule to another. And this is what insulation is for. Insulation tries to fill up spaces so that we don't have radiant heat transfer, or we don't have the convective looping, because there's no space in there for the air molecules to be moving. They have to move the heat by conduction instead. Air pockets are good insulators. So our insulation materials generally are full of air pockets, and that slows the conductive heat transfer. When we're talking about heat transfer, we can talk about it in building science as heat that transfers through the building envelope itself. And then we have some other terms, like a delta T is one term that we use a lot. That means change in temperature. And the larger the delta T, the faster the heat's going to transfer, because the hot's always trying to go to cold. And so this picture is just kind of showing that in the wintertime, if we keep our house at 75 and it's 0 degrees outside, our delta T is going to be 75 because we have a difference in temperature of 75 degrees. In the summertime, we have our house even, colder than I usually keep it, but at 65 and it's 105 outside, which sounds like a very large temperature. Our delta T is only 40. So our delta T in the winter tends to be a lot bigger than in the summer. And so we tend to focus on the colder times of the year of trying to trap that heat and keep it in. Although when we do that, we also keep the heat out in the summertime. And then air transfer. Air moves throughout a structure in several ways. But one of the things that causes the air to come in or go out of a structure is what's called the neutral pressure plane. There are pressures in a house, and when a house is experiencing a negative pressure, the air is going to try to leak into the house because nature abhors a vacuum. It doesn't want negative pressures. The pressure is always trying to go to 0. It's trying to equalize itself. So if you have negative pressure in a house, then the air is going to try to leak into the house to make up for that negative pressure. If you have positive pressure, the air is going to try to leak out of the house to make up for that pressure. And so on this slide, you're seeing the red, this red box with the dashes through it. That is our neutral pressure plane. And in this case, because we have punched a bunch of can light holes in the attic, and we've got a chimney with leaks around it, and we've got all kinds of leaks in our attic axis here, our neutral pressure plane is right up at the top of the house, which means that our warm air is all trying to rise and escape. And as the warm air rises and escapes, we become negative in the main part of the house, and the air tries to come in through all of our gaps and cracks and leaks inside the house. And at the same time, our attic is becoming pressurized, the air is trying to leak out of the attic. So what we want to do is move this pressure plane down in the house so we don't have such large negative pressures in the house to cause the air to leak in. Find my eraser. There we go. All right. And the thing about air transfer is when air does move in, it tends to bring with it moisture. Moisture comes in with the air. The moisture flow is very closely tied to heat and air. As our temperature in our materials change, then our dew point in the materials change. And so that if our material reaches a dew point, it can condense and cause bulk moisture, which we don't want. But even with an air leak, the air leak brings with it moisture molecules, and that brings in moisture into our houses. Air molecules are very big. They're not big enough for us to see, but they are big when you're looking at molecules. Water molecules are small, and they just go right along with the air molecules. The air molecules just bring them along with them. So moisture is continuously flowing throughout a house. And when you change a dynamic about the house, when you change one of these building science items about a house, then you change all of the other things. If you change airflow, you're going to change moisture flow and heat flow. If you change heat flow, you're going to change moisture flow and airflow. And so there's things that that these all interact and have corresponding changes, they corresponding effects with each other. And Brett, did you want to talk about that before I move on to thermal air barriers?
Yeah, and so what you're saying, Charlotte, really this basic foundational knowledge of building science, these areas here, this is one of the basic understandings that what we say, LEED green raters, green home inspectors, those doing sustainability inspections of homes really need to understand to be able to do this. So to become a LEED green rater, this is important to have 4 hours of training in this building science. So we have these opportunities available to do that. But to become the qualified energy rater, you need as well 4 hours of this building science training to understand the baseline of this. So specifically focusing on the LEED addenda 10443. If you look at that, and I'll drop a link in there and you'll have that available, you'll see out of the training required for that, besides having an associate's degree, that's one pathway. But another pathway is to have this 12 hours of training, and 4 of those hours, are focused on this building science aspect. So taking these quick concepts that Charlotte said and then going into more in-depth understanding. And really, I'm glad I'm bringing this up on the moisture transfer here, because in my opinion, that's really where this opportunity lies, I think, is to help ensure that our buildings are not exposed, to moisture over time and degraded. And so LEED has a lot of durability provisions in them. They have a sort of, checklist, and they give you guidance. But I think just having that foundational knowledge of how moisture is going to move and impact a building, for the sake of let's, set aside the minimum energy performance and energy efficiency and all that. It's really about durability. If we don't get, all of our homes designed or rebuilt to ensure that they're not rotting, what good is it? If you know anything about the weatherization programs in the United States, they don't help air seal and insulate homes that have a moisture deficiency. And so, as sad as that is, it's a reality that, when things aren't done correctly and things are falling apart, we can't invest energy efficiency into them. So I just wanted to point that out and say, this again is sort of just an introductory concept to that. And, we can move into the next step. So thank you, Charlotte.
You're welcome. Yes, these are introductory, and the training, as Brett said, it's 4 hours of these concepts, and so you will learn a lot on a deeper level, all of these concepts. So the next concept we're going to dive into are thermal and air barriers. Air barriers need to be fully understood, and the thermal barrier needs to be fully understood. And an example I like to give is the idea of a knit sweater and a windbreaker. If we are outside on a very cold, windy day and we have our windbreaker on, then we are cold because that windbreaker is not insulating us as well at all. There's no insulation in that windbreaker. It stops the wind, but it doesn't help keep us warm. We're still cold, that cold material against the skin. But if we put on our knit sweater, now we've got our insulation, we're put on our knit sweater, we go back outside on this cold, windy day, we are still cold. That wind is just going right through those holes in that knit sweater. It just blasts right through it, and you are still cold, and now you're getting the wind hitting your skin. But let's put on our knit sweater and let's put on our windbreaker over that knit sweater. Okay, now we can go outside and spend the day. We're gonna be toasty warm because our knit sweater is our insulation. It's holding the heat from our body in next to our body. And the air barrier is our windbreaker. That windbreaker is keeping the wind from moving through that insulation and dragging the heat out with it. So we are now toasty warm. We've got our air barrier and our thermal barrier. This is the same concept for a house. And the insulation is our knit sweater, and the air barrier is our windbreaker. One of the things we do to test the air barrier is we do infiltration testing. So our infiltration testing is going to measure how much air infiltration there is through the building envelope. So how much air is actually moving through the envelope, through all those gaps and cracks and can lights and anything else that we've punched into our building envelope, how much air is moving through. So one of the things that we do when we run an infiltration test is take a baseline pressure, because as I talked about before, with the neutral pressure plane in the house and with the holes that we have and with the wind blowing on the house, against the house and then going over the house and pulling air away from the house, we're going to have some pressures just from the nature, just from what's happening around the house. So we don't want to include that pressure difference in our infiltration testing because we want to know just for the envelope itself, how leaky is it? Not how leaky is it on a windy day or on a calm day, but how leaky is that envelope on any day. So we take the baseline pressure to rule out the stack and the wind effect, which is the natural pressures in the house. We also have to pay attention to what's the temperature inside and outside and what altitude is the house built at, because these things can also impact the readings on the infiltration testing. And we need to understand those so we can make adjustments based on those, so that no matter if a house is down at sea level or up on top of a mountain, we are looking at them the same way. We are normalizing the houses and the testing. So we take a look at that and we make adjustments as needed for home energy rating or for the energy rating index, or for any testing that we're doing according to the standards. There are a couple kinds of tests that we can do. We can do a single point pressure test where we just take one reading at 50 pascals of pressure is the pressure that we normally test our residential buildings at. And that is roughly equivalent to a 20-mile-an-hour wind hitting the walls, the ceiling, the floor, all of the surfaces of the house. And we can just take one reading at that. But with this research has found that has about an average of a 10% error, because you could have taken that reading right when a gust of wind hit the house, or you could have taken that reading right when everything calmed down. So there could be about a 10% error on average with that. And so then a correction would need to be made. Or you can do multi-point testing, pressure testing, which is where we will take measurements at various pressures in the house and then extrapolate from all of those different pressure points and those different airflow readings what would be the more accurate reading at a 50 Pascal pressure difference. So that gives us a higher level of accuracy, and that test can be automated. So we can see right here, this is a picture of me and my blower door when I still had dark hair, and running the test. We put a shroud in a doorway, have a very large fan that's going to pull a lot of air through that house, turn it on and pull the air through. We can measure how much airflow is going through that fan, and we can measure what the pressure is in the house and outside. And we can extrapolate from that the exact amount of air infiltration through that envelope. We can take this unnatural pressure at 50 pascals and determine what it would be on a natural day. So how much air is actually moving through the house when you don't put 20 miles an hour of wind against it. What that does is it helps us measure our envelope leakage of how much air is actually moving through the building envelope that we just talked about. And so what we want to make sure with our houses is that our insulation is protected from the wind. We need our windbreaker on our house. So we have our insulation, and then we make sure that all 6 sides of the insulation is covered with something. And sometimes people say, wait a minute, 6 sides, we've got the inside and the outside. Well, we do. We have inside, we have outside, we have top, we have bottom, we have right, we have left. So there are actually 6 sides to your wall or your wall cavity. And it depends on how the house is built exactly, but we want to make sure that we pay attention to all of the sides of the insulation and we're protecting it. Our air barrier could be something like this. This is Tyvek on the outside. It's for the outside air barrier. It makes a nice air barrier because it does stop the air from moving through. It's got a small enough weave that the air molecules aren't going to go through it, but it allows vapor to move through it, water vapor, the smaller molecules, so that the construction materials can dry. So any rain that hits it can dry. That we want to keep our houses dry so that they don't rot out, as Brett was talking about. And so, but the issue with our air barrier also is we have to make sure that we are putting it on correctly. Part of the air sealing inspection is making sure that it's installed correctly, and that it is repaired anywhere that it's torn. So here on this one, you can see that what they did is they put the air barrier, lapped it the wrong way. They lapped the lower part over the upper part, which will allow rain, if it gets back behind the siding, to just go right behind that air barrier. It's also a water barrier, bulk moisture barrier. It'll allow water right back behind that to that OSB board, which will then rot out. So that had to be corrected. That was a finding in an air sealing inspection. As well as that, all of the seams should be taped, and any damage done to our air barrier needs to be corrected. We don't want to leave holes in it. We're trying to make sure there's no holes in our air barrier. Sometimes our thermal barrier and our air barrier are the same material. So in this case, we've got some insulated sheathing on the outside of a house, and it is being both our thermal barrier with the insulation and our air barrier because it makes its own air barrier. But in that case, all those seams have to be taped, and all of the openings, the windows and the doors and the light fixtures, the electrical, the plumbing, anything that we punch through it, all needs to be sealed back up to that air barrier. Another part of our air sealing inspection would be looking at all the items on the inside of the building as well, because it's not just the walls and the ceiling and the floor that are I mean, that is our envelope, but we don't just have construction. We don't just have walls, ceilings, and floors. We punch holes in them all the time. So we have holes. We might have holes for can lights. Our can lights overcuts get covered up by a nice trim kit, but those need to be caulked and sealed, or those air molecules are going to find their way through there, right? And if you have can lights, the molecules are going to find their way through anyway, because they have gaps all the way around them, and they have holes on the sides of the housing to adjust light bulbs up and down. So they have a whole bunch of holes in them. When we put in can lights, we put in big holes. We also need to look for things like, this is a ceiling fan from the attic, and when you turn off the light in the attic, we can see the light from downstairs coming up because of the overcut in the ceiling fan. So these all need to be sealed, all these little holes, all these holes we drill in the top plate for wiring, for switches. That just connects the inside walls to the attic. Now the inside wall is actually an outside wall because the air can come from the attic, go right down through that wall, as well as the gaps on either side of a top plate. They need to be sealed. Sometimes we have flue pipes running up. This is actually going to be a chase that's going to have drywall all the way around it. But if you look here, even if they drywall down here at the ceiling level, we've got a big hole right to the attic. So that was part of the air sealing inspection. Said, okay, air sealing contractor, come over here. You need to foam and seal this hole that's going to be up here. And by the way, do you have any fire caulk? Because we also need to seal around the flue right here. We've got a flue pipe. They didn't have any fire foam at that point in time, so that didn't get sealed, but hopefully it got sealed before the drywall went up. It would have, otherwise it would have failed inspection. Here we've got an exhaust fan that didn't get an exhaust hose attached to it, so now that's a big leak of air. When it's running, it's blowing hot, humid air right into the attic. It's also uninsulating our attic for us, taking the insulation away, just blowing it right away. Adding all that humid, warm, humid air into a cold attic, potentially, which can condense. And now we're rotting out our building again. Not sure if too many people are putting in these whole house fans anymore in new construction, but they just have these lightweight louvers that lift up when the fan runs. And so this is not very much insulation, and it's wide open to the attic. And this one, in this case, actually was also digging insulation out of the attic of places because it didn't have enough exhaust ports on the outside to make up for the air that it was pulling into the attic. So the air in the attic was turbulent and was digging holes into the attic insulation. So we're looking for holes that we intentionally put in our envelope as well and trying to seal them as much as possible. Drop soffits are a big place where you can find lots of issues. This is a drop soffit with a couple of can lights in it. And this is what it looks like from the attic. It's wide open. You can see that they did not insulate the wall. They should have blocked the top of this off. There's wiring going in there for the light fixtures. So we've got a big air leak right to the attic. And this one is pretty amazing. We've got a big shower unit with a hot heat lamp on top. There's no insulation in this wall cavity. There's no insulation in the soffit. There's no insulation up here. So this is an air sealing and an insulation issue. When we do an air sealing inspection, a lot of times because we're looking at that envelope and we want our thermal barrier and our air barrier to be continuous and contiguous, we find not only air, but also thermal issues. Here is a nice chase, another flue chase, wide open to the attic on the top. And there's some, looks like water pipes and water fixtures there that haven't been sealed up. And so, I mean, the big hole, of course, is at the very top if that gets covered up. And this is what it looked like from the top, or that's, I guess, this one. But from the attic, you can see the chase is just wide open, these chases. So all of these interior walls that people thought were inside the house, in the middle of the house, and not connected to the outside world are wide open to the attic. They are all outside walls. They all need to be air sealed and insulated. The best way is to cover them up at the attic plane, seal them up really well, and insulate them. Then they do become interior walls. And our ductwork actually leads to air infiltration. So if we have air getting into our ducts, it is then being brought into our house. Or if we are blowing air out of our ducts out to the outside world, then we are pulling in air from the outside world because of the negative pressures that are caused by that. So some of the air sealing inspection is actually making sure the ductwork is sealed. You can see here, this is an unconditioned basement, and I can stick 2 fingers into the ductwork right there. So we're pulling in unconditioned basement air into our system and delivering it to our house, which means now we're pressurizing our house, which means we're causing the air to be pushed out of the house. This is a wall cavity that's going to be a duct. Lots of the parts of the country don't allow this anymore. Unfortunately, my city still does. However, when we make wall cavities into ducts, they are very leaky. And we can see they tried to kind of top off some of this with some drywall scraps, but there's still areas where once the drywall gets put on here, we're going to just have an opening right to the attic. We have, this is a panned duct, but you can see that they overcut at the top of it to run it up to the attic. This needs to be air sealed. We need to air seal that, or that attic air is just coming right down inside the wall. And then here is a couple trunk lines to an attic, which didn't get caulked at the ceiling. This was discovered when we turned on the blower door. The closet doors just flew open, and white insulation, fiberglass insulation snowed all through the house. So that needs to be sealed as well. We need to seal all of these duct penetrations, all these holes that we stick into our house. Here's a trunk line in the attic where the duct is coming disconnected. So now we're pulling in attic air into our house. All of that is air sealing, as well as a little bit of insulation in there, but our air barrier has lots of holes in it. They need to be inspected and they need to be sealed. Go ahead, Brett.
Yeah, so again, this is another one of those requirements to become the qualified energy rater, to have 4 hours of air sealing inspection training, which is part of the online training. Now, it's important to know that in the United States and Canada, currently blower door testing is mandatory, and a lot of that's done more through the robust HERS index rater training, or the verification and the energy verification inspector. I get that name wrong, sorry. But and then outside of the U.S., the blower door is ideal. You can get extra points for doing it. It can tighten up your energy models, but it is not yet a requirement in any other country besides Canada and the U.S. And so this is the air sealing inspection. And so part of it is, the energy modeling tools. In some of those tools, they have provisions in there to kind of gauge leakiness. So you'll have to work with your LEED quality assurance director to kind of say, based on your inspections, how leaky a building is, because normally you're inputting a blower door number. The other thing about the air sealing inspection that is really important is the compartmentalization. And a lot of people forget that in multifamily and attached row housing, this is not an energy issue as much as it is a health problem. If you have air leaking in between units, you could have who knows what, viruses, bad air quality going in and, degrading the health for somebody else. And so this is a health issue. And so compartmentalization is a requirement in all various aspects of LEED. And so you're also looking at those in-between units with the knowledge you have as a qualified energy rater for those air sealing inspections. So a lot of that will be more expanded upon within the more detailed trainings on how to do that. But that is, a very important thing to know, is that it's also a health issue for that. So thank you, Charlotte.
Okay. So then we are also inspecting insulation. The insulation inspection is another 4-hour component of the training. And the things we look for when we're inspecting insulation, we're looking for the insulation to be installed according to the manufacturer's instructions. This picture up here in the top is insulation that was installed upside down. So even though it's all put in and it's cut and it fits, it is not according to manufacturer's instructions. It is upside down. Part of the insulation inspection in the attic of a unit is to look at baffles as well. Baffles are there to move any air that's coming in through the intake vent, the eave vents usually in an attic that's brought in to pull the moisture out of the attic and keep it ventilated. The soffits will keep that air from going into the insulation. It should direct it above the insulation. Well, this is a unit that when we went in, it's a multifamily unit. Went in and measured, it looks like 16 inches of insulation here. The next day we came back in and this is what it looked like where we had been measuring. And this is because there was no baffle and the air just came in and pulled it all away. So the insulation contractor came back, re-insulated it, and the next day it looked like this picture over here. The mounds on the side just kept getting taller and taller and taller. We have mountains of insulation. Air coming in through soffits has quite the force behind it, and we need to make sure we keep that away from the insulation or we have uninsulated ceiling. Other areas where we'd have uninsulated ceiling could be things like this. This picture on the left is the top of an arched doorway. And the arched doorway is quite lovely from inside the house, but from the attic, it wasn't covered, it wasn't sealed, it wasn't blocked. So you can see that they did try foaming the wall at the end of the arched doorway, but we really need to block the whole doorway for the whole arch from the attic because these walls on either side above the arch are not insulated. So that this is an area that needs to be looked at. We also look at all the blocking in the attic along with the insulation, and you can see this is a very poor attempt at blocking chase. It didn't get sealed, so it's not air sealed and it's not very well insulated. Since they had holes in it, I guess they didn't want to put the insulation on it and try to fill up whatever was underneath there. When we do an insulation inspection, especially in an attic, we need to get in the attic and we walk all the way to the end of the attic. This is another multifamily unit with a shared attic across it. And so you can see the track there where we walked through the insulation to get way back to the back and be able to look at the entire attic. Once we got to the back end, we started to see it like this. We have a nice deep insulation here, although it is a little fluffed because it shouldn't collapse like this when you walk through it if it's at the right density. But when you get further down there, you see we're not even getting up as high as our ceiling joists. So we have to inspect the insulation throughout the entire attic and make sure that it actually was installed. There has been issues with some insulators standing in the scuttle hole and blowing insulation. And if they don't get all the way back to the end of the attic, it's not going to be fully insulated. We also look at walls. So this is a wall during pre-drywall. The drywall hasn't been put in yet. And all of these items in the wall with the insulation are compressing that insulation. You can see they did try to cut the insulation around the item, but they didn't fluff it back out. So we do have all this compression. And what that does when the drywall goes on, we are now going to have space between the insulation and the drywall. And what's going to happen with that space? We're going to have radiant heat energy, which moves really fast, radiant heat transfer, and we're going to have convective looping. So we're actually pulling the heat away very quickly, and we're giving it the opportunity to do that with all of these gaps between the insulation and the drywall. So this insulation needs to be corrected so that it can actually do its job and slow down the heat transfer. This is an example of what we call the Friday afternoon phenomena. We've actually been told by some insulation contractors when we've contacted them, we're there for the inspection and said, you just did not even insulate this area. What's going on here? Where they say, oh yeah, well, you know, we meant to. It was Friday afternoon, time to kick off work. We were going to do it Monday morning. By Monday morning, we forgot. You came in on Monday afternoon. It's still not insulated. Whoops. Yeah. So these are considered uninsulated, obviously. That needed to be corrected. And then, you know, we're looking at the quality of the installation of the insulation to make sure that it's actually being installed where it is going to do some good and slow down that heat transfer. This one I thought was an interesting photo because of the fact that they went to so much trouble to caulk and seal every single seam in there and try to get it air sealed, and then just stuffed the insulation in and didn't even fill it all the way full. This is below a window. So if it had not been inspected and been left like this and covered over with drywall, in about 5 years' time, that OSB below the window would have just rotted out, and we would probably have to be replacing the wall, replacing the window. We have, you know, condensation. We would have condensation underneath that window, and it would just rot that whole wall out. So insulation inspections are extremely important. Yeah, we look at the ceiling, we look at the wall. Did you want to comment on this, Brett, before I get to floors?
Well, I just wanted to point out, I appreciate what you said about the interaction with the contractor, right? And again, I always want to point out to both the contractors and our qualified professionals is that you want to have these situations that often occur built into your contracts too, because you know you're going to have to come back out and re-inspect it. That's a cost, and the contractor should assume that may happen, so they should have that buffered in too.
Mhm.
Mistakes happen. Nobody's doing anything wrong. I just wanted to kind of point that out, like,
Mhm.
assume when you are told to show up and the installation is ready, as you pointed out, it's not ready. So, someone's going to have to pay for those return trips. So, building that in. So,
Yes, yes. And actually, I do find that, especially with the trades, once they understand the building science behind it and they understand why it needs to be done a certain way, they're more than happy to do it exactly how it needs to be done. So they appreciate the education that they get on this too, if you communicate with them and work with them. So floors. Our code here says that your floor insulation must be in substantial and permanent contact with the subfloor. Just a basic insulation item to think about is insulation needs to be in contact with the surface that it's intended to insulate. That's how it works. It needs to be in contact with that surface. This looks like a beautiful floor in a crawl space, but when I put my camera up above the insulation, here's what I'm seeing. The insulation is not in contact with the surface that it was intended to insulate. It's not up against the subfloor, and there's no insulation at the end of each of these cavities. So this is an uninsulated floor. This all needs to be corrected. This floor does have some ties that are supposed to insulation stays, but they're put on upside down. You can see they're hanging down instead of pushing up. So the fact that they're hanging down means this insulation is falling out, which it already is, and it's going to fall out. Here's one that has a tie the right way, an insulation stay going upwards, but it didn't have very many of them. They're not holding the insulation, and this bat is already falling out as well. So the thing to remember is that gravity always wins. Gravity will always win. If it is not permanent contact, substantial and permanent contact, the insulation will fall out of a floor. There can be, or the best practice is to put some sort of solid backing on it. We need our 6-side air barrier. One of the things that does for us is hold our insulation in place. Okay. Oh, anything else about insulation before I move on to duct testing?
well, again, I just wanted to point out that this really rounds out the three items that you need to complete to become a qualified energy rater. The
Mhm.
building, 4 hours in building science, 4 hours in air leakage inspection, and 4 hours in insulation inspection. And so that's it. If you're not planning to do the blower door or duct blaster test outside of the US, that really is going to complete it. So there's going to be a lot more detail there about all of that. And there were some interesting questions that came up that maybe I'll throw out now before we move forward. And one of them really had to do with both the air barrier and the insulation as well. And so the question was, would it be easier to have a conditioned attic with insulation at the underside of the roof instead of having to seal all the canned lights?
If you're going to punch a bunch of holes for can lights in the ceiling, that probably is a much better option. You can have sealed attic. It does need to be managed correctly. It needs to be built correctly. We've seen a lot of failed sealed attics as well. So you need to pay attention to the building science, where the moisture is going, how the insulation is being held against the roof deck. But yes, that is a good way to do it. I've actually seen a sealed attic where the roofer and the roofer and the carpenter, they didn't understand that it was going to be a sealed attic, so they went ahead and cut vents through the insulation and cut vents into the attic. And so now it's a vented attic with no insulation because the insulation was all at the roof deck. Um, so yes, sealed attic is a good, in my opinion, is a very good method to use. It also gives you extra storage space, but you have to pay attention to what's happening with the heat and the moisture in that attic as well and manage that.
Yeah. And then the other question was about, attached single family row housing or multifamily. So we talked about air sealing the interior walls, but as far as insulation goes, to my knowledge, that certainly isn't a LEED requirement in the energy model. I think it's more of a local code or sound requirement, but can you speak to that a little bit, Charlotte?
Yes. you're not going to lose heat through a common wall unless the common wall is not well sealed, especially at the top and at the front and the back. That's areas that would need to be inspected for the air sealing inspection. The front, the back, and the top all need to be well sealed. But a lot of times code requires the insulation just for sound.
Yeah. So then, and LEED does have some extra points if you want to do sound quality testing. So those would always be a good idea to put those in. Though I imagine by the time you're doing testing, it's not the real world environment where someone's living next door with their, guitar going. So you may not get the perfect example, but there are air quality monitors. I have one. It actually monitors my sound over time, and I can see if my house is loud or not. And so that will be the future, inevitably, where we head. So look out for those things. But anyway, continue on, Charlotte. So
Okay. And duct leakage testing is another area that we test to see how our ducts are leaking. We basically have a smaller fan than the big blower door fan. We will pressurize or depressurize the duct system to 25 pascals of pressure. And that pressure is chosen because that is the pressure the ducts are going to be under when the system is running. And so we want to know how much of that conditioned air that we're pushing through the ducts is going to leak somewhere else. That we can measure the amount of air that's needed to hold the pressure in the ducts to hold it at that 25 pascals, and that's how we know how much air is leaking out of it. There's a couple duct leakage tests that are performed. One is leakage to the outside, which means it's telling us how much air is actually leaking outside of the envelope, and then total duct leakage, which tells us how much the ducts are leaking inside, outside, no matter where they're leaking. Because total duct leakage is important, because if our ducts are leaking, we're leaking all of our supply to the second floor and all of our return from the basement. We've now messed up the pressures in our building, and that causes infiltration and exfiltration. Even if all our ductwork's inside the conditioned space, we can change those pressures with our duct leaks. And not only are we then uncomfortable, but our house becomes very leaky. So we do want to test our ducts. And that is one of the optional items. And then Brett asked me to also talk a little bit about energy modeling. Energy modeling is something that that we need to learn. What we do when we are energy modeling is we have a software tool, and our software tool will generate for us what's called a reference home. We put in information about the home that is actually being built. We put all that in the software, and then the software takes that information and creates a twin house to it called a reference home. The reference home is generated by the software to meet the reference baseline, depending on what standard you're doing, what kind of what you want to compare against. It will create this reference home and then compare the actual house energy use that you've from all of the inputs that you put in to this reference home, which is built just to exactly meet the standards. And then you know if you're saving energy, you're using less energy than the home that's just made to exactly meet the standards, or your home is using more energy because it's not as energy efficient as the reference home that was built by the software. And so the energy modeling is a separate class, and it's very detailed and goes through. Right now, there's a HERS modeler, home energy rating system modeler certification training that can be taken, and it takes all the way through a lot of building science, all of the different parts of the house and the envelope, and what to expect, and then what data you need to generate this energy model and how to know if you're doing it accurately.
yeah, and that on the energy modeling again, that is required for the minimum energy atmosphere, minimum energy performance LEED prerequisite. So you're trying to hit a baseline energy rating index, or if you're doing larger multifamily projects, mid-rise projects, you're really looking at the ASHRAE standard. And of course, that's much more well known across the world than single family or low rise modeling. So that's where some of these tools like REM rate House Rater with the energy rating index, Ecotrope, and then there's the Florida Center. You know, these different tools can be used outside of the United States. But what we have to do when we're doing that is we have to find, you know, the equivalent climate zone in a case by case area basis. And sometimes we've had to like literally match it to an address in the US to find it. So each one of the models you pick will have different benefits, attributes, but you know, if you get training on one, you'll have a pretty good sense on how to do another. And then that will help meet the LEED minimum energy performance. And then also the optimize energy performance to gain those extra LEED points. And one thing I forgot to mention is when you're doing your quality review of the insulation installation, that will be an input into these modeling systems.
Mhm.
So if the insulation is put in very poorly, well, if it's very bad, it would honestly fail LEED in general. If it's okay, you'll just get a worse score, right? It'll reduce, and if it's the best, you'll get a better score. So that part of having that field knowledge is now how do I input that into the energy modeling software so it's appropriately, counting on how well the installation was done. So all that's kind of interconnected between the training, definitely in the HERS training or the BSI verifier training, that's all in there too. So thank you.
And there is a user-defined reference home that can be built. So that could be used outside the United States as well, where you can define your own reference home that says this is what it looks like if it's built just to meet the codes. You can tweak some of those numbers to make it match what's local for you. And then just, yeah, our wrap up here is just a wrap up summary of what is required for qualified energy rater. As Brett said, you need at least 4 hours of training in building science fundamentals. If blower door testing is being performed for the project, you need to be trained and get experience doing that. Air sealing inspections, 4 hours of that, 4 hours of insulation inspections. And then if duct leakage testing is going to be done for the project, you need to get trained and have experience doing that as well. You also need experience performing energy inspections on the testing, and at least 2 of the projects, 2 building projects with a similar scope of work. And that's something that Brett would be working with you on. And at least 3 years of professional experience in residential construction, which Brett will work with you to document. And then just a bottom note here. Additionally, the individual may not be part of the design or the construction team. And that is my presentation for today. Do we have other questions? I have a little time we can stick around.
Yeah, thanks, Charlotte. There were some other questions that came up, and real quick before we get to those questions, I just want to remind everybody that yes, this session is being recorded, and you can catch a recording of it here in the next couple of days. If you had to, you can check back at our YouTube channel when it is available. Or you can go there now, hit subscribe, and get an instant update when it's available, so you won't have to remember to look for it. If you're watching this session in the future, not right now, but on demand, take your quiz with an 80% passing rate to receive your continuing ed. If you're here today live and you've been here for the entire CEU approved hour and you're appropriately signed in and you take that survey that pops up at the end or is emailed to you when we're done, you'll receive your certificates from certs@gutenbergcerts.com. So check your spam to make sure you get those. And before we jump into those questions, again, a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, our over 400 members. We're trying to get to 500 by the end of this year. So we hope you will help us get there, as well as our top tier sponsors who are all making products that will help you achieve higher energy ratings with your clients. So Rheem for air source heat pumps, Build Equinox for smart demand controlled ventilation, and many of our other sponsors who are making these products to achieve ultimately sustainability goals. So Charlotte, one of the questions that came in is I wasn't sure if you had ever heard of felt being used for an air barrier. It doesn't ring a bell to me, but didn't know if that sounded like anything you're familiar with.
The only felt I've heard of is, like building felt, that can be used outside of concrete walls or um, under the your wall floor, your wall joists, but your bottom plate. But I'm not sure how good of an air barrier that would be. That's not really an air barrier because it is full of holes, and the air can move through it.
Another question came in about structurally insulated panels, and about the requirement of inspection of the seams prior to drywall insulation from the inside. Are you familiar with that being typically part of the air barrier inspection?
Yes, and that is part of the 4 hours of training. You will learn some about that, but yes, the um, air sealing and insulation inspection would both be part or be covered in that SIPS panels. The SIPS panel is a sandwich of 2 layers of OSB with insulation in the middle. But that insulation in the middle many times has holes drilled into it for wiring and plumbing and things like that. So the air sealing of that at the top plate needs to be checked, because if they're not sealed at the top, or any unused chases are not sealed, the air is just going to come right through them just like anything else. And the seams do need to be inspected and checked and make sure that they are fully sealed according to the manufacturer's instructions so that we don't get air between them and so that moisture doesn't move between them. With a SIPS panel, you could have some moisture issues that you might not realize you have until it gets pretty bad. So the inspections of those materials is very, very, very important.
And so, we talked about the qualified energy rater position for outside of the US. In the US, people are becoming HERS index raters or Building Science Institute verifiers. Can you just tell us a little bit about the sort of difference in the process there versus a qualified energy rater?
Yes, yes. To become certified as a home energy rater, it's closer to 100 hours of training rather than the 12. And it also includes several exams. You're going to learn more about combustion appliance safety and indoor air quality as well. And it includes an apprenticeship sort of period where you have to actually perform home energy ratings on a minimum of five units before you finish your certification. So you get some field expertise as well. So it's a little more rigorous. It takes a little longer. For the building performance verifier, I am not as familiar with the certification on that one, unfortunately.
Yeah, and I think there's a lot of the same requirements depending on,
Mhm.
as far as the comparison, the wide gap of significantly more hours for US based and the provision, the having that mentor. So the mentorship part of it and the certified rating part of it is not required outside of the US. It's ideal. It's something we can help with. You want to make sure you're doing it right? Because the last thing you want to have happen is show up on a LEED project, you're trying to get it certified and the modeling is all wrong. So it's certainly ideal, but it's not required. So just, wanted to point out those kind of key differences. So, well, Charlotte, I appreciate you staying on a little bit longer with us. Can you just remind us again, real quick, where people can go to learn more and, receive this training if they are interested either wherever they are in the world? So
Yes, you would go to energysmartinstitute.com and there's a course catalog. You can click on the course catalog and there should be a 4-hour course for the building science concepts. It's called the Building Science Fundamentals. And there's an 8-hour course for air sealing and insulation inspections. That one is likely not up yet, but it will be up by Monday. And then there's a 12-hour course that covers all of it for the LEED qualified professional. So you can choose to take the 4 hours Building Science Fundamentals and then follow on with the 8 hours of air sealing and insulation inspections, or you can choose to do it all in the 12-hour course at once.
All
We,
right, well,
is
go
it,
ahead, Ken.
I was gonna say, I think that our course catalog has all that. Is that right, Charlotte?
Yes.
Okay, I put a link in the chat about that. And
Okay.
I didn't hear you explain BPI versus ResNet, or did you? And I missed it.
That's a whole different.
Oh, well, that was a question though that Brett brought up. Is
Well,
that
we'll
No,
get to some of those other questions later, but yeah, the short answer is the BPI training is great. May even qualify those folks outside of the US for the training that they need. But it doesn't have any energy modeling component to it. So
yeah, it
uh,
does. Yeah,
uh,
that's sorry. But
well,
the main difference actually is that BPI does not have any quality assurance really of any kind.
that aspect as
Minimal.
well. Yeah, thank you. Yeah, it doesn't have the quality assurance, but certainly a fantastic organization, a fantastic training.
Mhm.
Certainly probably is qualifiable for our qualified energy rating. I know a lot of the BPI stuff has to be done in person too, which again
Yes.
isn't
Right.
bad. It's a good thing. It's just, they're very United States focused. So if you're in the US, absolutely get it. And the Homes Inflation Reduction Act in many cases funding has based themselves off BPI, though they're also allowing ResNet and BSI verifiers as well. So um, that's money you want to go after. So one of those is good. So thanks for bringing that up, Ken. But
Yeah, sure, sure. No
thank you
problem.
all, and take care and be well, and we'll see all of you next week. So thank you so much.
Thank you.
Thanks.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.